Alrighty, so hey y'all. Um, so pretty much how this is going to work is I'm just going to go over these different chapters to the power slides, and I kind of went through these and deleted a bunch of slides that I don't feel were super important, or they were just examples or whatever it was. And that way we can really just like focus on the things that I think are most important, and the things that he mentioned were going to be on the final. And so basically we're going to start right here with chapter 6. So a couple of things that I've written down that he said for sure was going to be on the final is one, the central limit theorem, which we'll go over here in chapter 6, the type 1 and type 2 errors, which we'll go over in chapter 7, how to fix a graph that is screwed using log, skewed, not screwed, and it's screwed up either way. But the definition of errors, heteroscedasticity, and then also the Greek letters versus the Latin letters, and then also talking about dummy variables. And those are kind of through all these different ones. So we'll go ahead and get going. So chapter 6, this is the one that really had a lot of like definitions. So it kind of just starts off and going over all of these things, the population parameter versus samples and everything. So obviously like populations are everything, samples are just like the small bit that you're looking at, and then going into random sampling and random sampling error. As far as how much he's going to really focus on these, I don't think a whole lot, simply because it's only a 40 question test. So I would, familiarize yourself with these, with like population, like population is the universe of cases. Population parameter is a summary of the statistics. A census is a complete set of cases. A sample is just a select group of the cases. Sample statistic is the estimate of the population parameter. Random sample is where any member has the same equal chance of being studied. What the random sampling error is, which is the extent to which a sample statistic differs by chance from the population parameter. Sampling distribution just shows how random sampling error shapes the expected values. And that's what, it goes over all these different definitions, and you guys should have notes on those. The next thing, this is the important thing that he was talking about, is the notation, specifically the Greek letters versus the Latin. And so the Greek letters are for the population parameters, whereas the Latin letters are sample parameters. So Greek is, everything out there. The Latin is just for the small group that you're looking at. So like you see here, like the true mean of a population. I honestly don't remember what all of these were, but I think, yeah, no, I know that this one is sigma. This one, I have written down that it's me.
It's mu.
Yeah, I think it's mu.
Yeah.
Yeah, so mu, mu. This one is sigma. This is your X bar. But so, you can tell the ones that look all weird, those are Greek. The ones that look like our normal letters, those are the Latin. And so X bar is your sample mean, S is your sample standard deviation, and N is your size. So this is one of the things that he said for sure is going to be on the final. So make sure that you know your difference between your Greeks and your Latins. So, and then this was like, the big question, how close is X bar to mu? Which is how close is the sample mean to the true mean. So now we're going to get into the central limit theorem. which basically it's just as the number of cases that you have increases, your shape is going to turn more and more like a bell curve. So you can already see that, and this is all because of the standard error. You know, it kind of comes up and goes down, but then when you get to, you know, and that was 100 cases, n equals 100. Oh, someone else wants in, Darren. Hey, Darren. So n equals 100, and you see how we have this bell curve. It's not super clean and everything, but it still has that overall shape. But then when you get up here to 100,000, it's got a much cleaner shape going all the way around. So, and then here it is, if we take an infinite number of sample sizes from a population of n members, the sample means would follow a normal distribution as it grows large. A normal distribution is that bell curve. So then here's also some more examples of the standard distribution. So like everything in this first column is a sample mean of 5, or a sample size of 5. And so it gets like, you can see it's a little bit wonky. And then you have a sample size of 15, it gets a little bit better, the bell curve. And then when you get to the sample size of 40, you get a real standard distribution. So is there any questions on central limit theorem? All right.
Nope.
So, and so a part of this central limit theorem and is like this whole thing about sample statistics to the z-scores. I kind of have a feeling that this is not going to be on the exam. Just most of like what I'm going off of is like what we really went over in class and what like we actually used versus what is something that he had to teach it to us because it satisfies a learning objective for the class. You know, you'll see that here. There's a lot of things that it's just like, oh, there's a learning objective you need to learn. So, yeah, so it's probably good to familiarize yourself with these z-scores. And it's basically understanding that the standardized, by standardizing the scores to this, your sample distribution is going to be closer to the actual distribution is the idea behind it. And so, yeah, that's, you know, z-score is a deviation from the expected value divided by the standard error. So then let's see here. These were all just talking about, once again, I don't think that this is something we're going to see a lot, the standard error of a sample mean. So the sigma is equal to 24.8 and n equals 100. And so that's like basically where you have sigma over n, where you would divide 24.8 by 100, and it equals 2.48. And so that's going to be your standard error. And so this is probably a good thing just to remember how to do, but I'm not 100% sure if it's going to really be on there. So, and it's just simply, and it's normally going to be the like a thing where he's going to say, you know, sigma equals this, n equals this. And so you just have to remember how to plug that in to get your standard error. Or some of these other equations he might have us do. He's just going to straight up tell us the, you know, sample error is this. So, but see, where does this get into? Same population. So I know that, yeah. Yeah, this I don't think is super important. It's just talking about how you can look at these two graphs and you can see this has a high variation, and that's why it has a flatter curve, where this has a lower variation. Most of them are right here, so it has that normal bell curve shape. And so, yeah, this is just saying the same thing, same population mean of 58, but A has a larger variation than B. So, this. And then this was just talking about how, you know, when you, depending on how many cases you have, you're either going to get like really scattered. This is at like 25 cases. Then when you get to 100 cases, it gets closer. And then when you get to 400 cases, your standard error goes smaller. And so, you know, all your cases end up a lot closer together, or all your sample means. So, and then this is just, again, this is kind of with the central limit theorem, where if we take an infinite number of sample sizes, they're going to be normally distributed, which is the bell curve, and that's because of random sampling error. So, and then this is population mean is 58, 48, so 58. So this is just that same equation, just written out the other way, where you're going to have the 24.8 divided by the square root of 100. And so this gives you your plus and minus, or your probability. So this once again is just about the z-scores, how to find them. I'm not super concerned with that personally. And then this is talking about, you know, just when they do the z-score, that's what that solid line is. So then we get into the whole confidence intervals of the 2.5% above and below. And then that was another thing, is that, you know, these z-scores are always centered on 0 with a standard mean of 1, or standard deviation. Shifts the mean to be centered on 0 and has a standard deviation of 1, is what the z-scores are. So then we're getting into the 95% confidence interval, where you have your sample statistic plus or minus the 1.96 times the standard error. I would not be surprised if we do have this equation on the test. And so it's most likely going to be, you know, it'll give you your X bar, you know, and he's probably going to give you your standard error. And so you're going to have to plug it in and, you know, do the X bar minus 1.96 times the standard error to get your lower boundary. X bar plus 1.96 times the standard error for your upper boundary. And then write out this sentence: we are 95% confident that the true mean lies between 54.1 and 63.9. I'm pretty sure that this will be one of the questions on the test. So just remember the 1.96. So, and yeah.
I have a question.
Yeah, go ahead.
Yeah, you said he'll likely give us the X bar and the standard error.
I believe so. Yeah.
Okay.
So I don't think he's gonna. I think it'll be like a word problem where it says, you know, you have a sample mean of, you know, in this case 59 with a standard, you know, just like this right here. Example: that's how I feel it's going to be
Got it.
written on there, is X bar equals 59 and SE is about 2.5. So that's how
Got it.
I think it will be. I mean, because otherwise, like, we did learn how to get the standard error. Which is going to be the omega, or sorry, sigma, over the, I think it's the square root of n. So this will give us the standard error.
Okay.
Right, so minus 0.4 standard errors of population. So yeah, see, this is the thing, is like the standard error, you have to know what the real mean is. Yeah, so that's why I'm saying, like, you have to know the real world stuff, and so that's why I'm pretty sure he's just going to give it to us.
Yeah.
So
Cool. Thank you.
not a problem. All right. So, and then this goes into the proportions. I don't think he's going to have us do this, but if he does, I almost feel like he would give us the formulas, because standard error versus standard error of proportion, and where you're using the square roots and everything. I feel like we're not so much going to have to do this as much as, like the problem that we did for that final review problem, which we'll go over that a little bit also, just as a refresher. But, so for the standard error of proportion, it's the proportion times 1 minus a proportion over the square root of the number of cases, the number of observations. So, and then this same thing, when you're getting your 95% confidence interval, you have to do the proportion plus and minus 1.96, the standard error. And then standard deviation, samples until the sample mean, and then 95% confidence interval. Yeah. I highly doubt that he's going to have us do these proportions, but that's it. So I'm going to go ahead and stop this video now, unless is there any questions going over chapter 6?
No,
All right.
I'm good. Yep.
All right, I'm going to go ahead and stop this now, and then I'll I just need to download the video file, and then I'll shoot a text for a new meeting. All righty.
Sounds good. Thank you.